Now we talk about molecules with a chiral center. For example, if you have a sp3 hybridized carbon atom, it can have 4 different bonding partners. And if we just have 4 hydrogen atoms, then it's rather easy because they're all equal. But if you have 4 different substituents, then you can find something called chirality. And therefore, we can imagine that we draw a plane through the molecule, which is indicated here. So here's in the middle is the carbon atom. Then you have 4 different substituents in different colors, and you draw this plane through the molecule. And if we have chirality, we cannot transform the molecule into each other by only rotating the molecule. And there is no symmetry center, so you can say that this molecule is asymmetric. Conversely, if you have a molecule where you have a carbon atom with only 3 different substituents, then you can draw again planes through the molecule, and then you can see that we have now a symmetry plane, and we can transform the molecule by only rotating. And this is important. So you should always be aware of finding the chirality in a molecule. So if we have a chiral molecule, then we have 2 versions of that molecule, and these 2 versions are called enantiomers. And what is an enantiomer? You can say that an enantiomer or 2 enantiomers have the same atom connections, and just on one carbon atom, the arrangement of the substituents is different. And here we do not have a change in physical properties of these 2 enantiomers. But what is different is the interaction with polarized light. For example, if one shows the rotation of the polarized light with an angle of minus 61 degrees, and here you can see that the other enantiomer shows the rotation of the polarized light with an angle of plus 61 degrees. And this is the difference between the 2 enantiomers. And what can also be different is the biological activity. For example, you can have a different taste of the molecules, but which is also much more important is that, for example, for drugs, it can be that one enantiomer helps you to better sleep, but the other is super toxic. And so you know that the 2 enantiomers look quite similar, but they can deal in a totally different way in your body. And if we then go to the next example, we can have a look on lactic acid. And here you can see that we have another name. We have a racemate. And this racemate is a mixture of 50% of the one enantiomer and then 50% of the other enantiomer. And this racemate is indicated by giving both the plus and the minus in the name. So plus or minus lactic acid is the racemate, whereas we have 1 plus enantiomer and 1 minus enantiomer. And the racemate has a different physical property compared to the physical properties of the enantiomers. And the reason for that is that we have this 50% mixture, and then, for example, the optical properties cancel it out. And also important when we talk about chirality is that we know how we indicate that we have a chiral center in the molecule. And herefore we use again the zip rules. And as already explained, we first assign the priorities of the substituents according to this rule. And for example, here we start with bromine as highest priority, then we go to fluorine, then to the carbon atom of the methyl group, and as lowest priority the hydrogen atom. And if you now want to assign the R and S configuration to the chiral center, after assigning all priorities to the substituents, you then imagine that you orientate the molecule so that the atom with the lowest priority is pointing away from you. Then you draw an arrow from the lowest priority towards the highest, and then be careful that you keep the relative positions of the substituents constant. And if you then draw this arrow in your mind clockwise, then we talk about a chiral center with an R configuration. And conversely, if we have this rotation anti-clockwise, then we have a chiral center with an S configuration. And for our example, we then have an R enantiomer. And what is now very important that you do not mix up R and S with plus and minus nomenclature, because R and S is the definition for the chiral center, whereas plus and minus is the nomenclature for the optical rotation of polarized light. And if you would like to train a bit the R and S nomenclature, you can use the word example 18.5. So this is what you do when you have only one chiral center in the molecule. But what do you do if you have more than one chiral center in the molecule? For example, here we can start with this 2s3r 3-amino butane 2-ol. We can see that on this top carbon atom we have a chiral center, and also on this bottom carbon atom. So, and if we now change the chiral centers in exactly the opposite ones, so we go from R to S and from S to R, and then we can say that these two molecules are enantiomers. And this is what you can see here. And if you only change, for example, one chiral center from R to S, but the second stays constant, then we have, for example, this error to consider. And then we talk about diastereomers. And diastereomers have no mirror plane, and also both molecules have different physical properties, and you can differentiate between the two different diastereomers. What is also possible is that we talk about a meso compound, and this can be seen here. A meso compound has a mirror plane inside the molecule. So, for example, you then have two carbon atoms with exactly the same substituents, and you do not see the diastereomers anymore.